that. Changes were made in the elevation or in the grade. Here's our again, it's a little hard to read, but we looked at residential site plans. Right? We had easements and setbacks, and differences in the line type that showed the as found or the existing grade and the finished grade. Right? We talked about on site plans. We talked about easements. Right? Easements either being someone who doesn't own the property is granted some rights to use it. You know, a utility easement would be the most obvious example, right? Where if there's a sewer or an electrical line or something running next to or through your property, then you can't build a permanent structure in that easement, right? Because the owner of that utility wants to have the ability to access that piece of your property, right? Setbacks, again, this ties back to zoning. You know, where you can build and where you can't build, you know, back from the property line. Again, here's another example of a floor plan, and a little hard to see here, but you see these section symbols. Yeah, here's this is something I think some of my lectures I keyed where they come from in the textbook. I should have done more of that, but again, in our building plans, we have indications of sections and details and tags for doors and windows, right? So again, from the floor plan, we can go to other places in the drawing set that have additional information. Right, these section views or detail references. So these symbols are used to tie the different types of drawings together, tie the plan to the section, to the details, to the elevation, to give you who are, you know, the person who made the drawings is given the ability to put those various pieces together. Right? Exterior elevations, again, this would be showing horizontal dimensions, right? Again, you can't see it here, but if you look in the textbook, you can see it better, right? This is showing elevations of various features of the building. Interior elevations, right? If we need to convey information about how stuff is laid out in a room, we might do it with an interior elevation. Again, sections are used to clarify details that we can't convey through a plan drawn at a larger scale, right? So the plan might be at 1/8 scale, and the section could be at 3/4 inch scale or 1 inch scale, right? That's a larger fraction, so we say that's at larger scale, showing more detail. And again, it's going to be taken from a plan or an elevation drawing and identified by a line that shows, you know, where that section is cut, and hopefully an arrow that points to show which way you're looking when you're looking at that section. Again, full building sections or wall sections. Or details, right? Again, that detail has a number in a drawing, so that should be keyed to something else. There should be some other place where you see that same number that tells you to look here for details. Again, made at a larger scale. I think that says 1.5 inches equals 1 foot. So that's giving. So here's where the architect is saying, this is how I want this piece of the building to be put together, right? Here's a steel I-beam and a bar joist bearing on that I-beam, and I'm guessing that's some steel roof deck and some rigid board insulation and the roofing. Okay, let's talk a little bit about structure, right? What holds the building up? We talked about the depth, how deep that footing has to be, right? The footing should extend a minimum depth of at least 12 inches below previously disturbed soil, or excuse me, previously undisturbed soil. So we want to dig down deep enough so we're getting down to soil that hasn't already been dug up and refilled or dug up and refilled, right? We also have to extend our footings at least 12 inches below the frost line, right? Frost line is the depth to which the ground freezes in the winter, right? We want to prevent that foundation from heaving or moving around when the ground freezes. Right, here's our frost line depths. I think we've said that 42 inches, give or take, is a frost line depth in Chicago. And you see as you move further north to a colder climate, that frost line depth increases or gets deeper. And as you move further south, that frost line depth diminishes. Right, you get, if you're like those guys in the video there, they're building houses in Austin, Texas. They probably don't really have to worry about the frost line depth because it's, you know, it's pretty minimal in that part of the country. So again, if you take a right, like our drawings for Sullivan or Marseille or North Home, and you pick that building up and move it someplace else, then the details of the foundation might change because the depth of the frost line might change. Right, the width of the footing has to do with the bearing capacity of the soil. We have the term load bearing value. I think a lot of our drawings have shown and a load bearing value of 2,000, right? 2,000 pounds per square foot. Right, that's how much weight that soil can take, how much force, how much downward force it'll support. Right, so again, here's our typical 2,000 feet, 2,000 pounds per square foot load bearing value. Right, note here, codes refer to the load bearing values as presumptive. Right, so that's a presumptive means, yeah, that's an estimate. So if you're building a residential structure, you'll probably know, hey, I've built houses in this area for a long time, and yeah, we did a soil test way back when, and we found that it's about 2,000. So we'll design everything around a presumptive value of 2,000. You know, if you're building a larger commercial structure, you're not going to guess. You're going to go out and have that soil tested, and you'll find out what its bearing capacity is. We looked at plenty of details for foundation walls or footings. Right, typically there's a keyway or something that ties footing to foundation wall. We have our rebar in there. Width of the footing is typically twice the width of the foundation wall. That's a good rule of thumb. Again, in our basements of Sullivan and Marseille, we also had column footings. Right, that column footing was thicker and wider perhaps than the foundation wall because it's taking a more concentrated load. We're taking that column load. Right, we have a steel beam running across the basement of Sullivan, and one or two places in that along that column or along that beam we have a column. So that column has a fairly concentrated load that's bearing on it, so that the footing has to be thicker and wider to carry that load. Again, if you go back and look at your column table in Sullivan, you'll notice that for a given soil type, as the column load increases, the size of that footing has to increase to support the load. Right, so again, if it's 2,000 pounds per square foot soil, if we double the column load, then the area of that of that footing would have to double to accommodate that additional column load. When we move from residential construction to commercial construction, right, to support the larger loads of non-residential buildings, we either have to make the footings bigger, wider, or we have to go deeper to get down to bedrock. I think we may have looked at how buildings were built in Chicago at the end of the 19th and early part of the 20th century. They used to build on wide footings called raft foundations, and sometimes that worked and sometimes it didn't work. Sometimes the building would settle or there'd be differential settlement. So again, if you've ever been to the auditorium theater, you know that there's a lot of difference in some of the floor heights there because there's been differential settlement in that building. So again, if we're going to build a larger structure, a commercial building, we have to go down deeper. We looked at a couple different methods to do that, right? Get down to bedrock, an auger cast pile or a caisson or a steel pile. Those are all ways of getting down to bedrock and carrying those additional loads that have to be carried in a non-residential or commercial building. So I made this slide here, Structural Systems 101, right? This isn't a class in structural engineering, but the same general concepts apply, right? Irrespective of whether we're talking about a structural system based on concrete or steel or wood, we're all trying to do the same basic things. We're going to take floor loads and transfer them to beams, or in the case of wood, we often call them joists. That those beam loads are going to get transferred to a girder, a larger member, and from a girder to a column. And ultimately that column load will get transferred down to a foundation or a footing. So those same general concepts apply again, whether we're building in concrete or steel or wood. We're looking for ways of taking loads and transferring them ultimately down to the ground or the bedrock or whatever our structure is bearing upon. Right, so if we do it with reinforced concrete construction, right, we have a slab and a beam and a girder and a column. Again, transferring those loads. If we do it in steel construction, again, here's our open web or our top supported K joist bearing on a beam, which is ultimately bearing on a column. Right. Again, in a metal building or in a structural steel building, often using that steel decking. Right, steel decking will be analogous to the subfloor in wooden residential construction. Right, that's what's taking the weight from the roof or the floor and transferring it to the joist. I think in some of our drawings, we've seen the terms live load and dead load. Right, it may have said something like, assume a dead load of 10 PSF. PSF is pounds per square foot. So dead load is the weight of the materials and the structure itself, and live load is the in the case of inside the house or inside the building, that's the occupants, the people, the furniture, the furnishings, right? Everything that's inside the house, that's live load. But we also have to contend with other live loads that are more site-specific, location or site-specific, right? Snow is a live load. That would be site-specific. Wind would be a live load that's site-specific. Seismic would also be a live load. Seismic means earth movement in the case of an earthquake. So again, your load characteristics, if you were building in Duluth or someplace that has a lot of snow, would be different than the load characteristics if you're building in Florida, where there's obviously no snow load, but a lot more wind load, which would differ than if you're building in Southern California or someplace that has seismic considerations, right? So you have to uh, tweak your structural design depending on the specifics of the site. Again, here we are back to residential framing. Those same concepts we just saw in the 101 slide apply here, right? We have a structural system where we're transferring floor loads to the foundation wall, from the subfloor to the joist, to the joist bearing on the sill plate, and ultimately to the foundation wall. Right, in our floor framing systems, we'll have to make allowances when we have an opening in that framing system, right? If we have a stair or something else, right? Here's platform framing again. We're going to be transferring those second floor loads to a bearing wall and then ultimately down to the foundation wall. Right, that load bearing wall or that bearing wall can be either the exterior walls of the house, or it could also be a wall, an intermediate wall in the middle of the structure. Right, that's ultimately going to carry that load down perhaps to that steel post or that beam or post that's running down the middle of the structure. Right, so when you're doing your renovation project, you need to know what's a load bearing wall and what's not a load bearing wall. Right, that non-load bearing wall you could demolish, you could tear out, and nothing's going to change. Right, you tear out the load bearing wall in the middle end and you could potentially have some problems. Again, here's our more conventionally framed stud wall. I should probably, not probably, I should find a better example here of advanced framing here, because they've got some extra lumber that those guys were just dumping on before. That was cripple studs and trimmer studs. Right, but again, this system is designed to take load and transfer it down. Right, that header is designed to take load above and make sure it gets transferred down to the foundation wall. Right, here's our roof framing again. Same deal, right? That system is designed to transfer roof loads to a bearing wall, then ultimately down to the foundation wall. Right, we're going to make sure that everything stands up. Right, we resist the wind and snow loads up here and transfer those loads again down to the bearing surface. Okay, getting toward the end here. Last couple units of the book, we talked about the MEP systems in buildings, MEP, mechanical, electrical, and plumbing. Plumbing, we talked about different materials that are used for water distribution piping, right? Copper piping. I think I showed a YouTube of sweating copper pipe. So we can sweat copper pipe. We can use press type fittings. Again, I think ProPress might be one of the trade names for these press type fittings. Again, the ProPress has a specific fitting and then a specific tool that's used to squeeze that thing together to produce a solid pressure tight joint. We can also use compression fittings for copper, smaller diameter. Talked about galvanized steel being a plumbing material. Again, galvanizing is putting a zinc coating on the steel to provide some corrosion protection. Galvanized steel is typically joined by threading, right? Threaded connection. So again, if the pipe fitter or plumber comes to your house and is working on a galvanized piping system, they might carry in with them these nipple trays with these short pre-threaded lengths of pipe that ultimately get joined together. Or if they're going to thread pipe in the field, they're going to have some kind of machine, either a hand tool or a power tool that cuts those threads in the pipe. Different types of plastic pipe, PVC and CPVC, right? Remember, if we have hot water, we're typically going to have CPVC piping. Again, plastic pipe has fittings, most often joined by solvent welding. So you'll often, if you look at a plastic system, there might be a little streak of purple running down from the joint, right? That's the solvent that was used to join that stuff together. Here's our drain, waste, and vent pipe. We talked about the fact that this plastic pipe does not have to have the same pressure rating as the distribution piping does, right? We're not, this drain, waste, and vent piping is not seeing the 50 pounds street pressure, water pressure that the distribution piping would see. Talked about the DWV system consisting of that vertical soil stack, the vent, the trap, and cleanouts, right? Each of those components plays a part. Right, here's kind of, again, DWV 101, right? We have a trap at each fixture, right? That trap, or that little bit of water, is keeping the smells, the sewer gas, from coming into your house. So you have a trap at each fixture, and you have a vent at the top to allow those sewer gases to escape and allow air to come in to make up when that stuff is going down the drain. And again, we have a clean out to give the plumber with the snake the ability to get in there and rot out that drain line from somebody that inadvertently flushed something down the toilet that didn't belong to go down the toilet, right? Or in my case, I'm doing a project or doing something in my basement sink in the workroom, and I'll stick something down the drain, and it's like, oops, I put something that it shouldn't go down the drain, or the little lint screen on the washer hasn't been changed, and that line gets plugged up, and I got to call the plumber and have the plumber rot out my drain line. Again, in plumbing drawings, we have this particular technique called an isometric to help represent or help visualize plumbing systems. We saw isometrics in our Delhi drawings. We saw more limited isometrics in some of the residential drawings, right? To some extent, that those details are left to the contractors, right? They're not drawn up by the architects or the designers. In terms of mechanical systems, and I'm watching the clock here, I should finish just about on time, right? We talked about different types of heating systems. Here's our forced air furnace. Different types of cooling or air conditioning systems. Unit, the textbook used the term unit cooling systems, right? Here's our window air conditioners. Our split systems or remote cooling systems, right? This is the condensing unit outside that gets paired with the furnace inside the house. Again, we're taking heat from, this condensing unit has a compressor in it that's moving a working fluid or a refrigerant, and that's moving the heat from inside and rejecting it outside, right? So if you have your air conditioner running outside and you put your hand on top here, right, it's going to have hot air blowing out of the top of that condensing unit, right? That's the heat that's that was inside your house that now you're moving outside, right? So you might get 100-degree air blowing out of the top of that condensing unit, and that's giving you nice, comfortable 72 or 74 or whatever it is air inside your house. It's another type of system, a duct-free or split system. Right? These are becoming more prevalent. So just as a single component that hangs on the wall and a condensing unit outside. We can also heat with water instead of forced air, right? A hydronic or water-based system. So that would have a series of radiators or baseboard connecting together with a piping system, ultimately going back to a boiler and pumps to move that water around. And our terminal units, or our units in the occupied space, could be baseboard, or we often call fin tube, or they could be radiators, right? If we live in older houses, we might have these old standing cast iron radiators. Or if we want to do something new and slick, we might use these newer style panel radiators. Or here's a hydronic floor, right, where we're circulating lower temperature water through tubes in the floor. And this is producing a pleasant, comfortable heating effect. We can do the same thing with electricity and electric radiant floor. In older homes, we can use these high velocity air conditioning systems as a way if we want to add or retrofit air conditioning to a house that already has steam or hot water, right? In our house, we have hot water radiators. I don't ever want to get rid of them because it's a good, comfortable source of heat. So when it comes time to add air conditioning, we're going to do a high velocity system like this. In commercial construction, a common means of conditioning that structure is with a rooftop unit, right? Wide range of capacities and sizes and types, rare for residential, common for small commercial, right? We had RTU1 and RTU2 on the on Delhi, right? One of them in the checkout area and one of them in the sales area, right? It's really easy. You can drop that system on the roof, and voila, you have heating and air conditioning and air movement. In both of these systems, the furnace and the rooftop unit, we also are filtering the air. Why are we filtering the air? I'll maybe when COVID goes away, I'll be able to ditch some of these slides here, right? Hopefully we're getting to the end of this thing, but when I made these slides up last summer, I wanted to remind people that they need to pay attention to the quality of filtration in their house or in the spaces that they're going to make sure that the filtration is good enough to get those nasty little things out of the airstream. Right? We've since learned that most COVID transmission takes place indoors. Right? So indoors, right? When we bring people back to schools and offices, hopefully that happens in the fall. Right? People that operate buildings are going to pay attention to the amount of air movement, the amount of ventilation, the type of air filtration, right? So they can get that small little coronavirus particle out of the airstream, right? Small things are harder to filter. Okay, home stretch here. Electricity, right? We use electricity for a lot of things because of its ability to do work for us, for its ability to do useful things, to have our computers and our phones and the light that's on my desk lamp here next to me, and the air conditioner, or the refrigerator that's keeping my food in our kitchen cool, and the air conditioner that will be running again in the summertime, right? All those we're using electricity to do useful work, right? The power is generally speaking the product, or X multiplying volts and amps. Amps is current, is the amount of electrons are trying to get through the wire. So we want to do more work. If we want more power, then we have to increase the voltage or the amperage, or both, right? But when we increase the amperage, we have to watch voltage drop, right? How the voltage changes from one end of the wire to the other. So we, generally speaking, if we want to increase the amperage, we have to get, the copper has to get bigger, has to get fatter, right? There's a limit to how big and fat that copper can get. Right, more amps equals more copper. Right, here's our number 12, our 12 gauge, right, for a general branch circuit, or perhaps 14 gauge for a 15 amp branch circuit, or perhaps 12 gauge if it's a 20 amp circuit. Right, in our house, if we have say a dryer, or electric dryer, or perhaps a electric oven, right, we have to get bigger, fatter wire, right? If we have a 200 amp service in our house, we're going to have larger wire than that. Same thing, longer distance, more copper. How do we account for that, right? Remember, power equals volts times amps, so there's a limit to what we can do on the amp side, so we increase the voltage, right? We go from 120 volts in our residence to perhaps 480 volts in commercial, and 120, or excuse me, 12,000 volts, in the lines overhead distributing electricity to our neighborhood, and even higher than that, the transmission towers that are bringing electricity to an entire city. The other thing we do, and this is still mysterious to me, even though I've been an engineer for a long time. Three-phase power is still somewhat mysterious to me. I know what it does and how it works, but I can't totally explain it. But again, in commercial construction, quite often we will have three-phase, because that allows us to deliver more power, as opposed to our single-phase residential, right? Here's examples of commercial wiring details. Three-phase, I think in Delhi was a 120/208 system. So we saw certain loads in Delhi, like the lighting loads would be 120. The rooftops, so 120 line to neutral, 208 line to line, right? So we saw, I think the rooftops at Delhi were 208 volt three-phase. So again, in the same wiring system in a commercial building, we can have both single phase and three-phase loads together in the same system, depending on how it's wired. In our residence, right, we have typically going to have 3 wires coming into our house, right? 2 black ones and an uninsulated silver one, right? 2 hots and a neutral. But those 2 hots are single phase, right? So we have single phase 3 wire. Our branch circuits and our lighting will be single phase. If we have an air conditioner or a stove or a dryer, or we happen to have a level 2 electric car charger, that would be 240 volts, but still single phase. And that's the end of my slideshow. Any questions, folks? Sorry, I buzzed through a lot of information fairly quickly. I'll post recordings of this. Again, I was just trying to highlight some of the high points of stuff we've covered throughout the semester.
Some of this the older material going to show up on the final?
Only to the extent that, well, yes and no, right? The knowledge is hopefully cumulative here, so I may ask a question that presupposes that you're understanding how basically how plumbing or electricity or mechanical systems work. So, um, you know, I'm my rationale for talking about stuff like this is just to give you the ability to understand what you see on the drawing. So um, you're going to be looking at a set of drawings and trying to interpret them. So having this knowledge will help. I think I suggested earlier in the class before you got here that if it was me, I'd take those drawings for North Home NH 1 through 13, and I'd spread them out and make sure that I got comfortable with what's there and how the various plans and elevations and sections go together, right? So when test time comes, you're not fumbling around. You have a good sense of where the information is located. I probably didn't totally answer your question, but trying my best here.
No, yeah, no, I understand. That was good.
Anything else, folks? Well, you're very welcome, Patrick. No, it's been my pleasure. Again, the final will be on Tuesday, the 11th at 7 p.m. during class time. So you can just go right to Blackboard and get on it. I'll be here, and you can email me or text me if there's any questions or problems. And again, if you have questions about anything, by all means, text me or send me an email. And it's a little weird here in a virtual environment. We you know, a little harder to say goodbye and good luck virtually than it would be if we were all in a classroom together. So I certainly wish you the best of luck. Hopefully this has been a good learning experience for you, and hopefully that you know, other classes and things we do at Triton will help you as well. So again, if you have any questions, please let me know, and best of luck on the final, and whatever else you choose to do in the business of construction. So good evening, everyone.
Good evening.
Thank you. I appreciate all your comments.